Okay, yeah, thank you. Yeah. I'm delighted to be here to talk to you about the topic, which is marine operational guidance using large-scale phase resolve wave predictions and network field sensing. And I'm delighted that we have been placed in the visions session of the day because it is actually something that we had thought about, talked about for many years. It's a vision or a dream we had, and I'm here to talk to you about two particular aspects which are quite theoretical developments on two topics related to this, predictability and capacity in terms of the sensing. And I'm representing work done at the laboratories of myself at MIT and Roland Bouffenet at SUTD. And both of us recently joined SENSEM in a project to develop a large swarm of sensing buoys. And what I'm going to share this afternoon technically has nothing to do with that project in some sense, because here we are talking about two very theoretical topics that will be able to take advantage of these swarms, which the development of which is the subject of the projects. So what is the idea, let me talk about, in terms of marine operational guidance and optimization? So the idea, fundamental idea is that historically we are able to improve or aid marine operations by predicting the ocean or the atmospheric environment in a statistical sense. You might think we can predict a sea state, and if the sea state is too high, we might suggest that we wait a few days until the sea state becomes lower so that we can make an operation. Now, the vision now here is suppose we are able to predict not the sea state, but actually the phase-resolved wave field. You can think in terms of function of space and time. At any time, I know where the crest is or the next trough would be, or predict a patch where it will be relatively calm, or I could navigate and sail my boat into that patch, right? So in order for this to happen, a lot of things need to be in place. I'm going to concentrate today primarily on this side of the picture, but this was the vision we had some years ago, namely that there are environmental input, you sense it, and you do large phase resolve wave simulations, and you predict the crest and the trough literally, by which you can then provide guidance or in fact autonomy to marine operations. Now, the benefit of doing all of that, and part of this also, we also would have computational models for the motion itself, including if you have, say, doing a load transfer, cargo transfer, the computational models will include the ship motions as well as the crane motions and so on. And the benefit, of course, is that you could increase safety. We might be able to substantially expand the operational and safety envelopes of these operations. We would increase efficiency, both in terms of cost and money, as I pointed out. And also, we might be able to achieve much higher speed and maneuverability if we know what the wave environment is in which our operations occur. And of course, finally, we would like to look at intelligent control, autonomous operations, field coordinations. We might have several vessels going at the same time, and they are all coordinated because the environment is given, and their motions subject to that environment is predicted. So what's required is our ability to provide sensing here and to produce these computations. And in recent years, we have been doing very large phase resolve simulations. I was having a lunch conversation, and they say, how large is large? And I say, well, 10,000 square kilometers routine, 100,000 square kilometers we can do, right? But maybe not real time. So I just want to motivate this vision, right? The vision, so I'll give an example. We have several examples, and some of these were really visionary, make-believe scenarios that we thought we could do, right? And so I just want to give an example. In this case, it's a side launch and recovery. Namely, you have a ship, bigger, say, frigate, and you would want to launch a RIB, for example, for rescue or whatever it may be. And typically for these, there are well-established criteria by which you can do a launch and recovery. In terms of ship motions, you may think of lateral accelerations, roll angle, pitch angle, and so forth. And so it would be really nice if we could, for example, have a prediction. Everything to the left of this is past, and everything of that is the future. And in what you will see is a video where this is the actual and this is a prediction. And the C state here, not the C state here, but the phase resolve C is being computed and predicted based upon sensing way up wave or wave stream, right? We may be covering the entire harbor, if you may, in the storm, okay? And what you would like to be able to do is tell the operator, here comes a window of opportunity. Green means the launch criteria is satisfied, red means they're not satisfied, and yellow means marginal, right? And so you could give the operator some warning, and they could decide when to launch that. So this is an actual calculation that we have done based upon this kind of calculation. So you can imagine this ship motion is being calculated. This is the side launch. These are the waves coming, and you can see this is rolling by. Now, the fact that the top and the bottom bars coincide means we're doing a good job predicting the waves, or hindcasting, right? And this is the forecast, since we don't know, we cannot predict the future, really, right? So you can imagine, for example, a green patch. Now, the movie is relatively long, and you can see that we cartoonize the color in the bay. If it's red, it means stop. Green means press forward and let the thing. So if you wait long enough, in fact, there is an opportunity where it came, right? And we predicted it, and where this vessel is put into the water, and it will sail off. Now, so what is required to achieve this kind of capability is the ability to do wide-scale wave sensing. The key question is, how much do we need to sense? How many sensing buoys do you need, right? Where, right? Does it depend on, of course it depends on the sea condition at that time, the wind and so forth, right? And so one of the questions that, in fact, we just saw this launch at sail while I was not watching. So one big topic, and it's some recent work that we have done, a couple papers that just came up, was to address this whole notion of predictability. The predictability question is posed as follows. Given a sea state, given a sea, not a sea state, right, and specific measurements, right, scattered randomly or moving, they could be fixed, they could be moving, they could be turned on and off. You can imagine you have a sensing asset, and you have to allocate your resources to decide where you want to put them in, right? What is theoretically, what is the predictable zone in space and time within which phase resolve predictions can be obtained? Right? So that's a realistic. In fact, more interesting would be the inverse problem. If I want to be able to predict, right, with confidence in a certain space-time domain, where do I need to have these measurements? So we address this problem, and again, I want to refer to, this is a phase resolve prediction, right? It's not the sea state. I'm telling you where the crest and the trough is so that I can sail my ship into or out of this, right? So this is an example where we have 7 sensors, right? And this is ocean wave field, and this is the reconstruction, which is at t equal to 0, right? And the dark blue means very little error compared to what we predict, okay? And the red line, which you unfortunately don't see very well, is the theoretical predictable zone. We call it P7, which means the predictable zone given those 7 measurements, right? And this is forecast. Based upon this calculation, we calculate the waves forward, and we are able to, the predictable zone at T11 is not the same as 0, of course, okay? It's smaller, as you might expect, it's forecast. And again, we numerically verify by simulation that, in fact, the error within what we say is predictable is very small. So what is the basis of some of these theoretical considerations? There are some remarkable results that we found. Seems trivial, but in practice, there's a huge implications. One of them is the following, that the predictable zone of 2 sensors is significantly larger, could be significantly larger than the sum of the predictable zone of each sensor, right? So this is an example. This is a particular case where we're looking at space-time. This is P1, if you may. This is P2, and this is P1 plus 2. Right? Now, this is just with 2 sensors. Now, if you imagine large number of sensors, we got a remarkable result. In fact, we are able to show that for J sensors, which could be a large number, the space-time volume of predictability scales as J cubed, if you know how to use them all together. So if you are not talking to each other and you use each sensor as if you own them separately, right, you will get much smaller number than J cubed. Okay, this is huge. And this is a theoretical result that we verified. And the proof is actually very mathematical in various set notations and theories, but we can actually show this particular notation here just shows that P1 plus 2 is bigger than P1 plus P2. All right, and so, and we did many nonlinear wave simulations to evaluate these cases. And in all of these results that you will see, whenever we draw a blue box, these are the errors in the predictable zone. And the blue is very, very small. And outside of predictable zone, you're not predicting, okay? And so the errors is fairly large. I pointed out that 2 is better than 1. A moving probe is much better than a stationary one, right? So predictable zone of moving sensor is much larger than stationary one. In this case, this particular pink area you see is for a stationary probe. And if you're now able to move the probe in a particular direction based upon the sensing, you can obtain a significantly increased. Okay, so P moving, right, Px of t is much bigger than Px0. Right? Now you can imagine then if you have a fleet of them, they're all moving, right? And then you have these j cubed plus this sort of, okay? And the question is, where do you want to move them, right? I just show you this particular example, right? And so you can have different scenarios, but in every case, if you're able to move, you should be. Not surprising, right? I mean, because special case of moving is not moving, right? And you should be able to do better if you're allowed to move, okay? So this Px of t is much bigger than Px of 0, right? And we have many examples we did by computations and by simulations, comparing, for example, stationary sensors to moving sensors, okay? And again, the movie takes a while. Let me just not belabor the point. Suffice it to say that the predictable zone is much larger if you're allowed to move. Okay. So given a directional wave field, optimally moving sensors can significantly increase the predictable zone. So this is another consideration. Now, turns out the placement of the sensors, as you can imagine, is also important and depends on the wave field. So it's not something you predetermine, right? You don't fix them like in a grid or something because you actually don't know what the wave is like, right? So this is an example where we have this is a predictable zone with a non-optimized placement of 8 buoys, right? And this is a particular optimized one, right? And we have theoretical ways of deciding how to do it based upon the characteristic of the wave you measure. It's not predetermined what the shape is, okay? Right? And you can see that predictable zone is much, much bigger, right? For the same asset and the same resources, right? You just put them in the place that is clever. Now, of course, in real life, it is life and death because you are operating here, right? And you need to know that could I not operate, right? Could I not launch, right? Could I not land a helicopter on the platform, for example? And so on and so forth, right? So the bottom line, the take-home lesson is that P optimized is significantly bigger than P not optimized, right? And we actually, I don't know if anybody from NUS, because they have a nice wave basin that just recently was completed. We actually collaborated with a former student of mine at Texas A&M. They have an OTRC, they have a basin, right? And we actually validated this in the field, okay? So this is an example where we are able to take, they have many, many measurements, and we take P, which are the ones that we use to calibrate, or if you may, to do the phase result prediction, and we use the other Q probes to compare what we predict, right? And so you can see that the fact that these curves follow as expected because they're using that data, but the fact that these follow is remarkable because these are predictions. So you can imagine if this was a particularly interesting region that you have concern about, and you judiciously placed the probes here, the P probes here, you could completely resolve the Q, phase resolved, right? So time's running short, and I gotta quickly move. Let me move on to a separate topic, which Roland Bouffenet and his crew in his lab had done a lot to address. And the question here is different, okay? So the question is no longer about predictable zone, per se, but what is theoretically the capacity of a network of sensors, right? So think in terms of sensors, and the sensors are covering a large region. They are not all end-to-end, right? They are talking to nearest neighbors, right? So the question is, theoretically, what is the limit, right? So in the SenSen project, we're actually building a fleet, we're testing it, but theoretically, we actually had no idea, right? What is the capacity? So there are lots of questions to ask. There are many, many benefits to swarming. Robustness, for example, a few of them could be lost, right? And then in terms of a network, the network is robust, right? You break a link, you continue. It's like you know, the cellular towers, for example, right? And it is flexible in the sense that it can adapt to changing environment, right? So you have suddenly, let's say the waves become much bigger here. You don't know that. You measure it, it becomes bigger. Then the network is flexible. They reconnect. So it's not a fixed network, right? topologically, they reconnect, right? So they get information from each other, right? And the question of scalability. If we could demonstrate with 50, is it obvious that you can do it with 500, right? And it's not obvious at all, right? So at the core of this scalability, flexibility, robustness is the question of what are the requirements for a swarm or a network to remain connected. Right? So if I want, say, consensus, which means I want everybody to be able to follow a particular direction, right? If my connectivity is broken, then I may actually have two different groups operating independently, right? Notice these are decentralized, right? Nobody is controlling, okay? They're all autonomous, decentralized, right? So the question can be addressed in this format. So you can think about all these buoys trying to do a particular mission, and under what conditions would they maintain mission, right? They're all in the same army, if you may, okay? Right? And so you can think in terms of a network, right? So this is a network graph, right? And this is a particular result. Now, this particular result says that if you are connected to 7 of your nearest neighbors, okay, then you can maintain this swarming robustness, right? Now, turns out the 7 is not universal. It depends on the size of the network, okay? So the question is, it's like, you know, what is it, the 7 degrees of separation, right? But if we didn't live on Earth, but on another planet with 10 times the population, is it still 7? What do you think? It's not, okay? Right, so that's a question, right? What are the properties by which we can understand this? And so there were some recent developments, in fact, this is a new result in the red box, and we're very excited about it, that addresses some of these questions. Okay, so according to Shannon-Hartley theorem, it is well known that the capacity of a network is related to the bandwidth, right, and to, if you made the signals to noise ratio, inverse of that, right? The more signal to noise, the bigger the capacity, right? And so this is a known result. But recently, Bouffenet et al. Obtain a result that show that you need a minimum bandwidth, okay, to maintain network connectivity, right? And this minimum bandwidth is a property of the network itself and calculatable from that, right? In fact, this is an explicit theoretical results. I mean, I've shown you theoretical results for a predictable zone, and now I'm showing you theoretical. This is particular result which shows that, in fact, that this minimum bandwidth, right, information theory bandwidth, can be calculated from the eigenvalues, right, of the graph Laplacian of the swarm network. So if you represent the network as a graph, you can calculate it mathematically, right? Now, please, this is topological connection, okay? If the swarm move doesn't matter. It's the way you connect them, right? Let's say 7, for example, will enter in a strong way into these results. So I know my time is very short, and I don't want to overuse the time. So what are some of these potentials? The potential is that if we could use these theoretical developments, right, we might be able to realize the vision, for example, of using lots of buoys, measuring waves, say in a harbor or something, and can significantly improve operational safety and envelope, right? Especially in rough weather, obviously, right? And so this is the only thing that's in common with the SenseM project per se, is that we have actually, in that project in the last year, we've actually built these, and we've tested them, field tested them, right, in the field, right? And so this is actually a photograph from some recent tests that we've done. And what you see is, I think we have total now here is maybe you don't count it, but I think it's like 51 of these guys, okay? And they are distributed, and you can imagine all of them sensing the environment, right, forming a network, and through our consideration would be able to say somewhere here, right, I can tell you exactly where the big wave is coming or calm, right? Okay, so this is actually a photograph of a swarm of intelligent autonomous network mobile sensing buoys monitoring the surface environment. Right. So with that, I want to thank you for your attention. Yeah.
One quick question. Yeah. The question: as your swarm gets larger, if you're using, say, acoustic or maybe spread spectrum in the radio, do you have to account for degradation of the communication channels among the different elements of your swarm due to mutual interference and degradation just with noise from the rest of the network?
Yeah. Yeah, no, that's a very insightful question, Harry. So what happens is that you wanted these measurements sensors to be flexible, to be mobile, and they're decentralized. So they are moving to where they think they should be, coordinated, right? But as the condition change, right, you need to reconnect the network. The network's not fixed, right? So you can imagine if I was in cellular contact with someone, this line would drop and the other line would pick up, right? And when these reconnections happen, for example, the capacity of the network also changes. So you have to take into account of that, right? It's possible that you are a Lone Ranger, you go all the way and you make some measurements, but you can neither talk to your friends, right, or distributed compute anything with them, right, and then you break down, right? So the objective actually is to maintain network connectivity, right, and robustness, right? So we mentioned flexibility, robustness, and something else. Scalability, excuse me, right? And so what the objective is, can you maintain that under the scenario you just described? So it's not a foregone conclusion. You need the topological connection of the network changes, right? And for example, I talked about predictable zone. The requirements of the predictable zone may be stressing the network, right? Because I need desperately to have buoys in a certain place to give me information, right? And we know from theory where I want that place to be, right? So we're calculating the wave field, if you may, right? We have proposed in the project to calculate distributed, okay? The computational wave hydrodynamics is computed within each sensors, or among the sensors, distributed, right? So the predictable requirement would force you or ask you to make certain motions or reconfigurations, right? And that will affect, for example, the network capacity, right? You cannot afford to do that and the network breaks down and you don't have the information, right? Right. So the answer is yes, it's an important consideration.
Thanks.
Thanks. Okay, thank you.